Hello, everyone. This is Professor Ma in these sections. In next sections, we're going to talk about how to integrate rational functions. And so to integrate rational functions, we basically break it out into pieces using the fundamental theorem of calculus. And that we integrate each piece. And of course, there are many different possibilities. But we will go through the basic techniques of integrating rational functions. Okay, and we assume we cancel all the common factors, so it's reduced. And furthermore, we assume the degree of the bottom, that is here, is more than the top. Because if it's not the case, we can do long divisions, and then we get a bunch of polynomial in the front plus some things in this format. So for example, we can break it up into integrating then therefore only this fractional part. And so then we further break up fractions of this type, PQ, P over Q, and with the degree Q is bigger, bottom degree bigger, we would do something called partial fraction decomposition. In particular, this decomposition is useful for us to do integrations, and there are other very useful uh, um, for this form, for this the decompositions. Okay. Of course, this composition is unique. That what I mean by that is one fraction formula would arrive at one particular decompositions. Okay. You and from fundamental theorem algebra over the real numbers, then every polynomial can be factored, and the forms that we factor is into first degree polynomial and the second degree irreducible. Okay, so in other words, if you give me a polynomial, it will can be some number times x minus something to a power, and that's our first degree, x minus something to a second power, and so on. So we got a bunch of these type, x minus something to a power. Then it comes in second degree, x squared plus, to a power that another second degree maybe plus or minus this form. Okay. Things like that will be like x squared plus 1. You cannot factor any further. Okay. So in other words, any real polynomial coefficient can be factors into this format. And of course, reminder, and this part is, you get a root, x equal to something, x equal to something. From each one of linear factor, you get root. Okay. And of course, when you get to this part, the square don't give you any real roots, but they do give complex roots if you want to do complex numbers. But we're not doing that. So this part basically stick like that. So for example, okay, this breaks up into x times linear, then times square form. This breaks up into linear times square, no real roots, only complex roots, times another linear times the second degree terms. Okay. And this simple second degree, it can be factored into two in linear in real polynomial. Just want to demonstrate that. Okay. And just a little reminder when we use how do we check? How do we check this has no real roots? Oh, it cannot be factors. You're going to use quadratic formula, and quadratic formula, and you check From quadratic formula, you're going to wind up with da 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 and the plus minus square of a negative number. Okay, over 2a. You're going to wind up with that. Then you realize, oh, no real roots. That's how we check it. Okay, so here's partial fraction decompositions. Suppose I have a fractions with the degree on the bottom bigger, and then I can break up these fractions into little pieces. And the little pieces consist of two types. Oh, each one then break up into two different cases. The two types is it consists of linear factors to a power with denominator. And the second type is that irreducible second degree powers, second degree irreducible terms raised to a power. Like for instance, this might be x squared plus 1 to the square. Okay. You say, well, what's this power about? What's the power? Oh, it depends on how many copies of that you have. Okay, so if this is a kth power is a factors of the q, then you will need one of the terms with denominators with a kth power. Okay, so that means if k is 3, then you're going to have a term look like that with cube. But since k is 3, then automatically imply it contains power 2 and power 1. So you must have also has a term with the second degree, also has a term with the first degree. Okay. So any kth power, you will need one of those. Second, for the linear terms, the top is a number. For the irreducible second degree term, on top is a linear function. I know it's kind of first time it's kind of hard to digest. Okay, so we'll go through that. Okay, we'll come back to these statements. Okay, for example, suppose the denominator consists of two linear terms. Okay, there's just two terms. And what's the power? Power, there's only one. Okay, I mean every one of them is first power. So therefore it breaks up into two of these with two numbers on top. Now, suppose I take one of the factor raised to a power, that I now have two factors with the second factor with the third power. Okay, now it breaks up into four terms. One, same as before, since x plus 2 is only first power, so you got one of that. Now, the other one, you have third power. You're going to need one that looks like this for each power. So, in other words, you're going to need for x minus 3 a fractions, x minus 3 squared a fraction, x minus 3 cubed. Because x minus 3 cubed is the biggest factor goes in there. So for the smaller power factor, you will need one of these type. Okay, so therefore you will have four breakups into four things. Now, okay. Of course, if I have a square over here, that I will need incorporate another number, say a, b, c, d, e, x plus 2 squared. Okay, that I will have 5. So it depends on how many powers linear terms you have. You will have how many terms on the right hand side. Okay, so this is what happens if the denominator can be factored into linear terms. Now, what happens if I have irreducible second degree where there's no real root, it's complex. Okay. Now, since this is degree 1, so therefore I only need one of these. I need for breakups of these types. Okay, and then remember, for the linear terms, the top is a number, but for the second degree irreducible, it's a linear function. Okay. There are two numbers you have to retract. What we're going to do is, of course, we're going to tell you what is number on what's on top. Maybe this is x plus 1, for instance. Then we need to figure out what ABCs are backward. Okay, that will give me x plus 1. So that's what we're going to do. Okay, but right now we need to know what does a breakup look like, so it will work. Go backward. Now, what happens if I raise everything to a power? Then you will need, in this case, it's 2 power 2 power 2. They will need 2 for each. You will need 1 of each fractions with each of its denominator. Okay, and for the linear ones, for the x and x plus 2 related to these linear factors, you only need numbers on top again. But for the square ones, irreducible square, you will need linear on top. So now you got 6 different numbers you have to figure out later on. Okay. Let me see that. Okay. Now let's talk about, in all these cases, how do I recover ABC? Suppose I tell you Px, like I said, is x minus 3. And then how do I recover the A, B, C? Well, in this case, I have to cover 6 number EF. So when you add them together, they actually wind up to be x minus 3 over that fractions. Okay. And there are two ways we do these. Okay. And well, now we do 2 ways. There's one way we do this, and that's probably the fastest, using paper and pencil. Okay, and here's how we do it. Oh, by the way, a lot of textbooks give you a longer way of doing this with system of equations. Yeah, that's a very systematic way of doing things, but might not be the fastest way. But things can be done a lot faster using these methods. Basically, you fish out using simple methods some of the number first. A, B, C, D, E. Maybe you can get A and C and D. There's an easy way to fish some of them out. In particular, I'll show you which one can be fished out. So you find those numbers first. You put them back into the form, clean it up, then try to fish out the other one that's harder to do. And the other one, you do it by comparing the left and right hand side the coefficients. So the second way is expand and match coefficient methods. Okay, so here we go. Oh, by the way, make sure you check the condition, the degree. This degree of down below is 2. It's a second degree, and below on top is 1. So, therefore, I can break this up into partial fraction decompositions. Okay, what format? It's going to break them into linear terms with numbers on top. Okay, these both numbers I can fish out real easily. How? Clear the denominator first. You get a lengthy looking equation. By the way, this is supposed to be identical. There's nothing to, you're not solving for x. You're supposed matching numbers to solve for the a and b. So the identical, they work out to be 2x plus 3. Okay. And the easy way to do this, the first way is I can evaluate. What do you mean evaluate? This is called evaluation method. Choose a number you can plug in on x, so that you can get the number A or B. Okay, so with one number you can plug in to make things disappear. Well, plug in 3. On the left-hand side, you are going to get 15. On the right-hand side, notice when plugging 3, you make this disappear. And these become 5, and then tell you what B is. Okay, this method we call the evaluation method. You plug in something, the formula is supposed to give you the same thing. And you plug in things that's easy to calculate. You don't have to plug in 3, it's just 3 is easier. Then the other number is easier to plug in to figure out, compare to left and right is plug in minus 2. Then you get A is 1/5. And voila. Okay. And when can you use, okay, and so basically this is what we're going to do, okay, for all the partial fraction decompositions. That is the first step we do is this. Okay, now we know what the form of the decompositions shall be. There shall be 4 fractions. This to the first degree over here. Therefore, there's only one of these. Okay, okay. And there's a third degree of that. Therefore, there's a 3 of those. But fortunately, there's no square, so they all numbers up there. So there's a number, number, number. So this is the format it will break up. So that's the first things you have to do correctly is to be able to read what formats it breaks into. Once you have that, okay, then the next thing we're going to fish out the A, B, C, D. Which one can I fish out? Well, let me clear denominator first, okay? So multiply by cross by the denominator. And that's what I get. Okay, then what number can I plug in to make things disappear? Well, there are 2 numbers, and one of them plugging 3, the other one is plugging 2. So there are 2 numbers. In other words, this linear one of first degree, okay, we can make them disappear. Again, fished out. Sorry, we can fish out. Okay, make one disappear. So plugging 3, again, fish out 1D. If I'm plugging 2, I'll get A is minus 1. Okay. And this as much as we can get an easy by evaluation. Okay, now what? Now we have what we know. This is something we do math all the time is we get partial answer, we put the answer back into the original problem, and we have a shorter or maybe easier problem. Okay, so let's put it back and take a look at what it looks like. Okay, put minus 1 back in the equations. I know, no, so this is where you have to do some algebra. So you're going to do some cleaning up. So we'll and then we're going to put everything we can, the B and C, we're going to leave on this side. And we're going to take these things, everything we can expand and find out what it is. We're going to put on the other side that we know explicitly what it is. So do some algebra. Okay, so put everything on the left-hand side except B and C. Now I cannot evaluate, but I'm giving 2 or 3, and both sides will come out 0, 0, 0, 0. So evaluation will work. Okay. So are there any other tricks? Yeah. Okay. I can look at, usually at this point, I'm going to compare coefficients. Well, how do I compare coefficients? You start from both ends one at a time. You could. Okay. For example, okay, we're going to look at one of the first things you always look at the biggest degree terms, okay, or the constant, depends on the form on the right hand side. And that's 1x cubed. And then you look at the right hand side, where do you get x cubed? You're not going to get x cubed from there. You get x cubed from here, multiply. In other words, b times this, when you expand, you're going to get bx cubed and something else. And that's supposed to match up the x cubed. Okay, the rest match up. So b has to be 1. Then you put b1 back into the equations, clean it up, do what we, okay? Well, actually, you don't even have to clean up. You can just leave at that, and now let's try to match up what the n number has to be, okay? On the left-hand side, coefficient is minus 24. On the right-hand side, how do I get a number term? The number term is 1 times minus 2 times minus 3 squared. 1 times minus 2. You know, if I expand this, it will be x squared and plus 9. Okay, so 1 times minus 2 plus. So in other words, this okay, it's going to be minus 18 for the constant terms. Okay, there'll be something x in the front, but the constant term multiplies minus 18 over here. And the constant term multiplies the number c times 2, 3, minus 1, 6c. So if I only look at the constant terms, these three terms pops up. These tell me what c is. Okay, so you solve your sigma minus 1, and then this is the decompositions. Okay, now let's put some square in there. Put a 1 irreducible square. Then you have to remember what the form of composition is. Is one of these and one of that. But for the x squared irreducible, you need linear, you need bx plus c up. Clear the denominator. I can plug in a number minus 2 to get one answer, to get the a. Okay, so I get a is equal to 1. And I put 1 back into here, and I have this equation, clean it up. Okay. Well, you can clean up or expand it to compare. Then essentially you compare the terms again. You can get b is minus 1 and c is equal to constant terms. So you can read the sequential logic how to get the highest degree term number and get the coefficient numbers. Okay. And this is just for one irreducible. Okay, no. So the three numbers to solve here. Let me remind you again. Okay, it's A, B, C we solve. So we get the A easily, B and C by extracting the coefficient by comparing two sides. Okay. And here is again breaks up into three irreducible. So this one I can easily pick up A, B, and C by evaluating. Okay, you put in 0, then these are if you put in 0. Okay, these are roots 0, 1 minus 1. You put 0 in there. Put 0 for x in there, so these pieces disappear, and put 0 in there, put 0 in there, equal 1, a is 1, and a is equal to 1 pops out. Okay, then you do the same thing, and then you can easily get it. Okay. And here's go to square case. Okay, it's basically the same methods. Okay. So I'll let you read the other part of the PowerPoint. It goes through, let me see, I think I have another one that has, yes. So anyway, you wind up these decompositions. And just for the sake of integrating one format of fractional formats. Okay, and so this is a particular one format, and you can see using fractional decomposition how to think about how to do this. And that's it. That's partial fraction decomposition. Okay. Now, of course, for instance, the next thing we're going to do is say, hey, how do I integrate x dx? And then the answer is easy by integrating these. And these all become log, log plus log plus log. So in the antiderivative of rational fractions, you see a lot of terms of log. Okay. Then for the square terms, irreducible, we will talk about that also later. Okay. But that's it. That's partial fraction differentiations. Until next time. Bye-bye. Stop. Have a good day.